Okay, hi everyone. Welcome back. We're going to do a bioenergetics problem now. If you'd like to see the problem in its entirety, it's actually one of the chapter questions at the end of chapter 5, question 6. The question presents one of the steps in glycolysis, the conversion of 3-phosphoglycerate to 2-phosphoglycerate. And we are going to calculate some free energy changes as well as do an analysis of the equilibrium constants for this problem. Now, the conversion of 3-phosphoglycerate to 2-phosphoglycerate can occur in both the forward and reverse directions. The equilibrium constant for the reaction as drawn is 0.165. All right. Now, remember the K equilibrium constant is the concentration of the products divided by the concentration of reactants. All right. So those are some of the numbers that we already know going into this problem. Now, a couple of other things to note about this question that we're going to explore is that the question asks us to not only consider the equilibrium constant, but also to consider that in red blood cells, the concentration for 3-phosphoglycerate is 65 micromolar, and the concentration of 2-phosphoglycerate is 4 micromolar. And so we're going to ask ourselves, in a cell, would this reaction occur in the forward direction or the reverse direction? And that's going to be important because of the availability of sugar in the cell and the metabolism of that sugar, whether or not it will actually proceed. And so part A is first going to ask us to calculate the standard free energy change of the reaction. Now remember from your textbook, page 123, that the standard free energy change is actually equal to minus RT times the natural log of the equilibrium constant. And this collapses to minus 592 times the natural log of the equilibrium constant. We can use this equation to calculate for this example what the standard free energy change is. In this case, minus 592 times the natural log of 0.165. All right? And ultimately, what this becomes is 1,066 calories per mole. Now, when we look at this, we have to analyze it and understand what a positive standard free energy change really means for the situation. We know that because it's positive, this is going to mean that the 2-phosphoglycerate is going to be the predominant species at equilibrium. It also means that under standard conditions that this reaction is not spontaneous. If it were spontaneous, it would have a negative delta G 0 value. Okay, so now that we've calculated the standard free energy change, we need to re-examine things. I'm going to write the equation again up here in the top. And the second part of the question, part B, asks us to calculate the standard free energy change. Whoops. I'm sorry, not the standard free energy change, but just the free energy change. The standard free energy change would have a naught as a superscript to this. So this should immediately speak to you as having to do with those experimental values that were given at the beginning of the problem. and I'll just write them again. Remember, the numbers that we're to take into account are the concentration of 3-phosphoglycerate and the concentration of 2-phosphoglycerate, okay, in a red blood cell. And so this part is a little bit more complicated. I'm going to try to write a little smaller so I can fit it on here. But delta G is equal to the standard free energy change plus 592 times the natural log of 2 pg over 3 pg. Now, we already calculated the standard free energy change on page 1, and remember what that was, 1066 calorie per mole. All right, and this is going to be plus 592 times the natural log of the concentration of products over reactants. This becomes 1066 cal per mole plus 592 times the natural log of 0.061, which equals to 1066 minus 1655, which equilibrates out to 589 calories per mole. It is negative. Notice that sign. Since it's a negative delta G, it is thermodynamically possible under the conditions stated. It is spontaneous under those conditions. So, when a red blood cell has 65 micromolar 3-PG and 4 micromolar 2-PG, the reaction as written will proceed in the forward direction and is thermodynamically spontaneous. The final part of this question, part C, asks if 3-PG, the concentration of 3-PG, is held at 61 micromolar, how high can the concentration of 2-PG get before the reaction ceases? This means that as written, 3-PG being converted to 2-PG no longer happens spontaneously. So the free energy change under the indicated conditions is no longer going to be negative. What it's asking is at what point is it going to switch in a positive direction? And so in order to calculate this, I need a nice clean page. What we're going to do is first write our equation. Oops. Delta G prime is delta G0 plus 592 times the natural log of the concentration of 2-PG over 3-PG. Okay, that's our starting point. we're talking about a situation that switches from negative to positive. And so what we're going to do is we're going to set delta G prime to 0. And we're going to solve for the concentration of 2pg. Okay, this is going to be our unknown, and this is going to be set at 61. So we're going to write this into the equation. We already calculated what the standard free energy change was. Remember, it's positive times the natural log. The concentration of 2pg is still unknown, but the concentration of 3pg is 61 micromolar. Okay? Now I'm going to draw those big parentheses there because in order to deal with a natural log, you have to do something special mathematically to the equation. If you don't remember, that's why I'm showing you now. We have 1066 plus 592. Now look what happens to this equation. We take the natural log of the top and we subtract the natural log of the bottom. Then this breaks down and we can do a little bit of math here. The natural log of 61 micromolar is going to be 4.11. We can start solving here, so we're going to subtract we have plus 592 times the natural log of 2pg, and then we have a minus 2,433. 0 equals minus 1367. So we subtracted 2,433 from the 1066 to get minus 1367 equals 592 times the natural log of 2pg. Excuse me. Okay, oops, I noticed here I put an equal sign there, and this should be a plus. Okay, so now we have to solve for this. I'm going to rewrite it just so that we don't lose our space here. Okay, let's bring the 1367 over to the other side. So we're going to add 1367 to both sides. Now, at this point, we have to get rid of that natural log. So we're going to take the exponential, the e value, or the inverse log of the natural log. And when you use your calculator and take e to the 1367th, or the inverse log, what ends up happening is, oh, I skipped a spot. I am sorry. Let's divide both sides by 592 first. And we get 2.304 equals the natural log of 2-phosphoglycerate. And then we take the E function and we get 10 micromolar equals the concentration of 2pg. All right, so what does all this mean? Well, remember, 3-phosphoglycerate goes to 2-phosphoglycerate. What we did was we asked if we were to clamp the concentration of 3-phosphoglycerate at 61 micromolar, at which point will the direction of reaction, so now we're thinking here, when will it want to go this way? And instead of in the forward direction. And so based on our calculations, we figured that at equilibrium, so when delta G0 prime is 0, we just calculated that the concentration of 2-phosphoglycerate will be 10 micromolar. And so at that point, the reaction stops going forward. It actually doesn't go backward either, it just stops. So we can safely say that any concentration of 2Pg greater than 10 micromolar will give you a positive delta G prime value. And that will be not spontaneous under those conditions. So that is the question from the homework at the back of chapter 5, question number 6. What I would suggest is that you look over that problem, change the numbers around a little bit, and work it out for yourself on a piece of paper like I have done here for you to see if you can work through it and understand the process, and I think you'll be all set. If you have any questions, feel free to stop by during office hours or make an appointment. Thank you.